Bismillahirrahmanirrahim. Today we will be talking about thermodynamics and energy. This lecture is also a part of the lecture series regarding the course of thermodynamics, having the course code of PHY331. Actually, in this lecture, we will try to elaborate the relationship between the course of thermodynamics and energy. If we see, thermodynamics is actually the science of energy, and energy is the ability to cause changes. So the name of thermodynamics actually came from two Greek words. One is called as thermi, that is called heat, and the dynamics means power. So this is actually thermodynamics that are dealing with the heat energy. We have the conservation of energy principle that is present in thermodynamics, that is actually the first law of thermodynamics. So during an interaction, energy can change from one form to another, but the total amount of energy remains constant and the energy is conserved. So this means that energy cannot be created nor it can be destroyed. So even the first law of thermodynamics also says that energy is a thermodynamic property. Here we are looking towards the picture where there is a initially when the object is at height, and some height, it has potential energy of 10 units while it has no kinetic energy. When it is fall down, so gradually its kinetic energy increases while its potential energy decreases. So at some particular point like this point, its potential energy is equal to 7 units while its kinetic energy is equal to 3 units. So the second law of thermodynamics also describes the quality as well as the quantity of energy. So it also describes the actual processes occur in the direction of decreasing quality of energy. If we are looking toward a hot cup of coffee that is at 770 degrees centigrade, and that is placed at room temperature, whose temperature is around 20 to 25 degrees centigrade, so what happen? The heat will flow from hot coffee toward the environment, and this flow will continue until both achieve the same temperature. So this is some traditional or natural way of transferring heat from hot body toward the cold body when both the bodies are brought in thermal contact with each other. So we have classical thermodynamics, that is actually a macroscopic approach to the study of thermodynamics that does not require a knowledge of the behavior of individual particles, unlike statistical mechanics. So it provides a direct and easy way to the solution of engineering problems, and it is used in this text. Basically, in classical thermodynamics, we are only interested in the measurable quantity instead of the actual participant that is playing the main role in it. If we look toward the statistical thermodynamics, that is actually a macroscopic approach, and it is based on the average behavior of large group of individual particles. So we are not interested in statistical mechanics in this course because this course is not devoted to that. But anyhow, statistical mechanics is a separate course that will be studied in earlier classes. We use different dimension and units in the thermodynamics. So any physical quantity can be characterized by dimensions. So the magnitude assigned to the dimensions are called as units. So just like we use the basic dimensions such as mass m, length l, time t, and temperature t are selected as a primary and fundamental dimension, while others such as velocity, energy, volume are expressed in terms of primary dimension, are called as secondary dimension or derived dimensions. So we have some special SI unit for that. We have special or different unit for measuring different values. Initially it varied from country to country because there was relative measurement in different countries, and different units were used for that. But when system international was developed, and some standard units were found that was used throughout the world. So we have simple example of just like a typical match yield is about 1 BTU of 1 kilojoule of energy if it is completely bound. So this is some simple example of that. We have the dimensional homogeneity is also there. So all equation must be dimensionally homogeneous, and we can convert the one unit system into other unit system, because initially some units over there, so there is some relationship between the units, and this relationship is helpful in converting the value from one unit system into other unit system. Just like we have force units of, for example, can be expressed in terms of kilogram meter per second square, and that could be expressed in different conversion as well. We have some basic thing that is very relevant to the thermodynamics, and that is actually the basics of thermodynamics, and that is the systems and control volumes. We have system, that is actually a quantity of matter or region in space chosen for study. So anything that is in consideration or in observation or in investigation is considered to be a systems, and that is chosen for particular study. We have surrounding, that is the mass or region outside the system. The region that is not included in a system is called as surrounding. So surrounding is out of the system, and that is actually the mass or region outside the systems. We have boundary, that is actually the boundary between the system and surrounding. The real or imaginary surface that separates the systems from a surrounding is called the boundary. So that is actually the boundary or the barrier or the region or the space in between the system and surrounding is called as the boundary. So the boundary is of two types. It might be fixed or movable, and it might be open or closed depending on the mass transfer, energy transfer, maybe nothing transfer. It is may be considered as a open or closed depending on this various configuration, and in some cases the piston is movable, or in some cases it is fixed. So we have closed system, that in which mass is controlled. So in that a fixed amount of mass is there, and no mass can cross the boundary. I means no mass can enter or leave the systems in this particular case if we are considering a closed or isolated system. Here we have some example of that, in which mass cannot cross the boundary of a closed systems. There is a closed system and mass m is enclosed inside there. So what happen? The boundary of the system is adiabatic, so energy can transfer, it can go out or enter the systems, but the mass cannot transfer because the piston is fixed, and the mass can stay inside the, I mean the quantity of matter remains the same inside the system, while the energy can transfer because the system is adiabatic. We have another system where there is a moving boundary. In that particular moving boundary, there is a closed system with a moving boundary. If there is a flame that is heating that, so the mass is constant but the boundary is moving, so it is moving up when the pressure inside the cylinder increases. And some other example where gas, the magnitude of the gas remains constant, and while its pressure increases or decreasing depending on the particular configuration. So this is something about system and surrounding and the boundary of a system. This figure clearly elaborates the system and surrounding. So this is actually the system which is under consideration. This is the surrounding. Outside the system is called as the surrounding, and this is the boundary, that is actually the boundary in between the system and surrounding. We have open system as well, where there is control volume and a properly selected region in space. So it usually encloses a devices that involve mass flow, such as a compressor, turbine, or nozzles. So both mass and energy can cross the boundary of a control volume. So this is some simple example of the open system, and the control surface is the boundary of a control volume. So it can be real or imaginary. So a control volume can involve fixed, moving, real and imaginary boundaries as well. We have some example here. An open system or a control volume which with one inlet and one exit. So we have this system that is actually the open systems. So here we have another example of a control volume CV with real and imaginary boundaries. So we have some real boundaries over here, and there is some imaginary boundaries that is also there. So another control volume with a fixed and moving boundaries as well as real and imaginary boundaries as well. So that is also another. If we are increasing the pressure, so the piston may moves up, and if we are decreasing the pressure, so the piston will move down, so depending on that particular configuration. So we have properties of the systems that are different. There are different properties of the system that are described the nature of that particular system, just like we have actually the properties, the characteristic of any particular system. So some similar properties of this particular systems are the. So some properties of the systems are the, just like we have the pressure, temperature, volume and mass are actually the properties of the system. So properties are further characterized into two, whether the properties are intensive property or extensive properties. So intensive property are actually those properties that are independent of the mass of a system, such as temperature, pressure and density, while extensive properties are those properties whose value depends on the size or extent of the mass. We have some extensive properties, just like the mass. If when we have a portion of cylinder that have some pressure, volume, temperature, pressure and density. So what happen if we divide that particular cylinder into two? So what happen? The temperature of the two portion or two compartment remain the same. Even the pressure of the two compartment remain the same. The densities also remain the same. So what would change it? So it means the value of temperature, pressure and density remain constant in both the compartments. So these are actually the intensive property. While if we look toward the mass and volume of this cylinder, so what happened? The mass is divided into two, and even the volume is also divided into two. So it means it is changed with changing the size of the compartment. So that is actually the extensive property of this particular systems. We have specific properties as well that are actually extensive property per unit masses are called as a specific property. Just like we have specific volume V divided by capital V divided by M, just like E is equal to capital E divided by M. So we have density and specific gravity, that is also a part of that. So density is actually the mass per unit volume, and it is expressed in the unit of kilogram per cubic meter. And specific volume is actually the mass per volume divided by mass, and that is 1 over density. So specific gravity describes the ratio of the density of a substance to the density of some standard substance at a specified temperature. That is, if we consider just like usually at water at 4 degrees centigrade. So specific gravity will be equal to gravity divided by gravity of H2O, and the specific weight is the weight of a unit volume of a substance, and that is equal to R is equal to sigma G. So density is the mass per unit volume, specific volume is the volume per unit mass. So here we have the specific gravities of some of the substance at 0 degrees centigrade, and from this equation we can calculate if we have the volume that is equal to 12 meter cubic and its mass is 3 kg. So what will be its density? And its specific volume, its density will become 0.25 kilogram per cubic meter, while its specific volume will be equal to 1 over density, as its magnitude will be 4 cubic meter divided by kilogram. So this is something, and here we have the specific gravity of some of the substances at 0 degrees centigrade. We have different states of any particular system, just like we have equilibrium and non-equilibrium state. So equilibrium is further divided into three different types. When the property of the system remain constant, then we consider that the state is in equilibrium, the system in a state of equilibrium, while if the property of the system remain change continuously, so we say that the system is in inequilibrium state. So in equilibrium, in equilibrium there are no unbalanced potential or driving force within the system. We have different sort of equilibrium, that is the thermal equilibrium. If the temperature is the same throughout this entire system, so that is actually the thermal equilibrium. So in mechanical equilibrium, if there is no change in pressure at any point of the system with time, so that is the mechanical equilibrium. And phase equilibrium, if a system involves two phases and when the mass of each phase reaches an equilibrium level and stays there. In case of chemical equilibrium, so what happens? If the chemical composition of the system does not change with time, so there is no chemical reaction occur. So this is actually the chemical equilibrium of the system. We have a system at two different states. Here it is state first, its mass is 2 kg, temperature is 20 degrees centigrade, while its volume is 1.3 meter cubic. Similarly, in the states 2, its mass is 2 kg, temperature is 20 degrees centigrade, while its specific with its volume is 2.5 meter cubic. So this is some particular case. Even here we have this is in another configuration of a system reaching in thermal equilibrium. We have different parts of the systems that is at different temperature to each other, and when it is brought in it is already in thermal contact with each other. So what happen, if we look initially before, its temperature at one end is different, just like here the temperature is 20 degrees C, here is 23, here 30, here 35, here 40, and here 42. Is all the parts of the systems is in thermal contact with each other. So what happen, the heat will flow from the region of high temperature toward the region of lower temperature, and this will continue until all the places achieve the same temperature. So here at the final configuration is that we have 32 degrees centigrade throughout the entire body. So we have some state postulate. So the number of properties required to fix the state of a system is given by the state postulate, and the state of a simple compressible system is completely specified by two independent intensive property. If we have simple compressible system, and that if a system involves no electrical, magnetic, gravitational motions and surface tension effect. So this is an example of state of a nitrogen in fixed by two independent intensive parameter, that are its temperature, that is 20 degrees C, and its volume is specific volume is 0.9 meter cubic divided by kilogram. So we have some processes or cycles that are involved in any particular thermodynamic system. So a process is actually any change that a state any change that a system undergoes from one equilibrium state to another equilibrium state is named as a process. So we have path for that, and the path is the series of states through which a system passes during a process. So to describe a process completely, one should specify the initial and final state of any particular system, as well as the path it follows and the interaction with the surrounding. So we have quasi-static and quasi-equilibrium process. When a process proceeds in such a manner that the system remains infinitesimally close to the equilibrium state at all the times. So that is actually the process. Here we have slow compression, that is quasi-equilibrium, and here we have very fast compression, that is non-quasi-equilibrium. So we have a process between state 1 and state 2, and the path of any particular process is available here. So process for that is actually diagram can be plotted by employing thermodynamic properties. The coordinates are very useful in visualizing the properties. So some common properties that are used in coordinates are temperature, pressure, and volume, and when we draw it, so that is called as PVT or PVT diagram for that. So the prefix ISO is often used to designate a process for which a particular property remains constant. Just like we have isothermal process in which temperature remains constant, we have isobaric process where pressure remains constant, we have isochoric process where volume remains constant, and cyclic processes are there, and a process during which the initial and final state are identical, that is actually the cyclic process. So we have steady flow process as well, that is actually for the term steady implies no change with time. So if the opposite of steady is the unsteady or transient. So a large number of engineering devices operate for long periods of time under the same condition, and they are classified as a steady flow devices. So steady flow devices are the processing during which a fluid flows through a controlled volume steadily. So this is something like a steady flow condition can be closed approximately by devices that are intended for continuous operations such as turbine, pumps, boilers, condensers, and heat exchangers, power plants, or refrigeration systems. So this is some of the system where we have steady mass flow. The mass is coming at this portion and mass going out at this portion. So this is some particular steady flow process. A fluid property within the control volume may change with position but not with time of that particular system. So we can see how the properties of the systems remain unchanged with the steady mass flow throughout the entire systems. So we have temperature and zero law of thermodynamics. That is actually zero law of thermodynamics says that if we have an object that is in thermal equilibrium with two different objects, so the first two objects will be in thermal equilibrium with each other. Here in this example we have iron that is initially at 150 degrees centigrade, and we have a copper in thermal contact with each. As temperature is 10 degrees C, so what happen when both are brought in thermal contact with each other? So heat will flow from iron toward the copper, and this flow will continue until both achieve the same temperature. So here in this figure we can see that iron and copper both have the same temperature. So this is something about the third law of thermodynamics. So we have different temperature scales that are a general and simple thing, that is just like we have Celsius scale, Fahrenheit scale, and Kelvin scale that is used for measuring the temperature of any particular systems. And these scales are measurement in these particular scales are interconvertible. I mean, if we can measure values in one scale, we can easily convert it into other systems. And these are actually the relationship that are used for measuring, for converting the value from one temperature systems, from one scale system toward the other scale systems. So we have some absolute pressure, or the gauge pressure, or the vacuum pressure, that is actually the mass per unit volume, and the absolute pressure is the actual pressure at a given position that is measured relative to the absolute vacuum. Gauge pressure is different, and it is actually the difference between the absolute pressure and the local atmospheric pressure. So most pressure measuring devices are calibrated to read zero in the atmosphere, and so they indicate gauge pressures. And while vacuum pressure is the pressure below the atmospheric pressure, is called the vacuum pressure, and the pressure increases with depth because when the variation of density with the elevation is down. So we can easily measure because the pressure of a liquid at rest increases with depth as a result of the added weight. So this is something at room where we have filled with a gas. The variation of pressure with the height is negligible, while pressure in a liquid at rest increases linearly with the distance from the free surface. So here we have Pascal law, where the pressure applied to a confined fluid increases the pressure throughout the same amount. So what happened, we can use this Pascal law for lifting of large weight by a small force by the application of Pascal law. So that is a common example of what we are using in daily life is hydraulic jack. So this is something about today's lecture and a general discussion about thermodynamics and energy. So thank you very much.